Indeed, it is awesome to be in Vermont. I did grow up in Essex Junction and left when I was 18, but come back occasionally. So I don't choose where I go for these DLP lectures. So when UVM popped up on my schedule, I was over the moon. But then, of course, didn't actually get to spend the weekend with my family because my flights were all canceled. But that's all right. Here I am now. So yeah, I want to talk to you about the oxygen cycle. I don't think she's here right now, but I had a wonderful meeting with Julia about the carbon cycle. You know, we hear a lot about the carbon cycle, but the oxygen cycle is equally, if not more important to the evolution of our planet, evolution of life on Earth. And so that's what I'm going to address today through the rock record. This is a thin section of a peridotite from Tonga, and this thin section is showing us spinel, olivine, and orthopyroxene. And those three minerals in equilibrium set the oxygen activity, the chemical potential of oxygen in the rock. And so by analyzing minerals and analyzing earth materials, we can learn something about the power of oxygen to engage in reactions, oxidize materials, or the lack of oxygen to be a powerful influence in the earth. And so, okay, why would we as geologists broadly, not just petrologists or geochemists like I am, but why should we all care about the oxygen cycle? Well, it enables a habitable planet, okay? At the end of the day, we all breathe oxygen in this room. Oxygen is an important gas in the atmosphere. The partial pressure of oxygen in the atmosphere, anyone? 21%, 0.21 is the PO2 in the atmosphere. And rocks record a PO2 as well. There's no actual gas in the rocks, but you can imagine the partial pressure of oxygen in equilibrium with a rock, and that's the PO2 that rock records. And this is really obvious in a volcanic system, okay? So here we have gases dissolved in a magma, and you can see we have carbon monoxide. You add oxygen to that system and you get carbon dioxide. So you go from a poisonous gas to a life-giving, habitable planet gas like CO2. You move from explosive hydrogen gas, you add oxygen, and you get life-giving water. And this is made possible by the partial pressure of oxygen in the magma chamber. So our planet is good at having magma chambers with an oxygen partial pressure that favors the release of gases that enable a habitable planet. I think this is a really important concept because, in fact, the equilibria, okay, is kind of teeters. You know, we're not so far on the oxidizing side that these gases are a given. And of course, we do have examples of outgassing of methane and hydrogen sulfide. Okay, so we're right at an oxygen partial pressure tipping point in magmas generated by melting the planet's mantle. Okay, so I'm going to switch from talking about oxygen partial pressure to talking about oxygen fugacity for the rest of the talk. Okay, and I always say, you know, for oxygen fugacity for seismologists, if rocks were an ideal gas, we would just be calling it partial pressure. And because there are no gases in rocks, we come up with fugacity, which just stands for fudge factor, essentially. It's a way of not technically or thermodynamically being able to call it PO2, so we call it fugacity, or the escape tendency of oxygen in a system. And we're going to take one more step from PO2 to FO2 to talking about relative oxygen fugacity in a solid system. So for the rest of the talk, we'll pretty much leave oxygen fugacity land and talk in terms of what are called the solid buffers. So because we're interested in the oxygen fugacity recorded by igneous rocks, and igneous rocks come out at all different temperatures, right? Rhyolites are a really different temperature, say, than basalt. We don't want to worry about temperature. We want some reference frame to talk about oxygen fugacity. And so a really good example is the iron wustite buffer. When you have iron metal in equilibrium with wustite, FeO, you set, when these two are in equilibrium, you set the oxygen partial pressure, the oxygen fugacity of the system. It defines the oxygen fugacity at a given temperature. It's a higher oxygen fugacity at higher temperatures and a lower oxygen fugacity at lower temperatures. So if we want to remove temperature from the equation, we can talk about things in terms of log units above or below this solid buffer. okay? And for most of the Earth, magmas on Earth, we're going to be in this range, about a couple log units above the quartz fayalite magnetite buffer and the nickel-nickel oxide buffer. Nickel-nickel oxide is exactly analogous to iron wustite. So we can kind of think about the core mantle boundary, okay, as having, well, you know you have iron metal, so we have some kind of like minima defined by iron wustite. And we also have nickel-nickel oxide, much more oxidizing conditions. One thing I want you to notice about this graph is that oxygen fugacity, unlike a lot of other really important intensive parameters like in pressure, temperature, varies by orders of magnitude. I mean, look at this. We've got 15 orders of magnitude just on planet Earth. I mean, forget other planets, okay? Oxygen fugacity varies by orders of magnitude from the surface of our Earth to the core of our planet. And so it has tremendous dynamic range to affect petrological processes. And the petrological process we're going to talk about, focus on in this talk, because one of the goals, kind of the overall research goals of my group right now, is to understand how oxygen fugacity varies in space and time in the Earth, from ocean islands to mid-ocean ridges, back arc basins, and arcs. And so we kind of have looked at basalts from all these different environments to map how oxygen fugacity might vary in the solid Earth, what time scales, what spatial scales. This talk, I'm just going to focus on the arc setting. And there's going to be a couple of very broad questions I want to look at. One is I want to kind of look, we're going to see in a moment that there are some zeroth order statements that we can make about the oxygen fugacity recorded about by arc rocks versus, say, mid-ocean ridge basalts. And I want to understand how much of the oxygen signal recorded in basalt at arcs is imprinted by processes in the crust and shallow processes, and how much is imprinted by the mantle wedge that melts underneath, and how much that might be influenced by this process of subduction. So one of the really big overarching questions is, okay, we erupt basalts here at mid-ocean ridges. They're relatively reduced, representing a relatively reduced mantle. But then they spend millions of years on the seafloor in contact with a water-rich, oxygen-rich environment, the ocean, okay? And this crust gets waterlogged, it cools off, becomes dense, and subducts. And then it's the dewatering of this slab and the transfer of fluids to the mantle wedge that enables arc volcanism. So how much of that oxygen signal then matters to the fact that these arc rocks are more oxidized? Okay, the second big theme of this talk is going to be the oxygen fugacity control on the generation of calc-alkaline magmas. And I want to bring this back to like petrology 101, okay? Continental crust is similar in composition to andesite, okay? It's a calc-alkaline product. So this is the only ternary, I promise. It's the only ternary in the whole talk. It's an AFM diagram. We have alkalis, MgO, FeO, basalt plots about here. And there was, a debate back in the day, in the early part of the last century, between the Fenner trend and the Bowen trend. This is Norm Bowen, okay? And Fenner, you notice that Hawaii, you had that's not me. In Hawaii or in Iceland, you'd have basalts that would differentiate as you subtracted olivine, for example, from the basalt, as they differentiated towards lower MgO contents, higher silica contents, the iron would increase before eventually plummeting down, go up and then down, tholeiitic trend. Bowen noticed that basalt could follow the calc-alkaline trend, or the Bowen trend, classic reaction series from basalt to andesite to dacite to rhyolite. And that was seen in the Aleutians and in Mexico. Okay, continental crust is on the calc-alkaline trend. And so the reason this is like the holy grail of Earth science. Of course I can say this because it's what I study, right? Why do we have continents on this planet? If you're an alien, okay, and you fly in your spaceship to the Earth, there's a couple of things that you notice. Water, surface water. So if you're ever in an exam, surface water's got to be one of your answers. And the other is bimodal topography. Okay, we have continents and we have ocean basins. We essentially have continental crust and we have basalt, and it makes for a dichotomous bimodal distribution. And our planet is the only planet like it with plate tectonics. And we live on continents, so we want to understand what is the origin of continental crust. So how does this link back to oxygen fugacity? Okay. Kennedy, who was an experimentalist, kind of weighed in on this Bowen-Fenner feud by doing some experiments. And he said, with the hope of resolving the conflicting views of Bowen and Fenner, the present writer took to remelt and crystallize some natural basalts in laboratory crucibles. It became immediately apparent that the same basalt could be made to follow the Bowen trend or the Fenner trend, depending on the partial pressure of oxygen. So under reducing conditions, you would get a trend of iron enrichment, and under oxidizing conditions, you would get a trend of iron depletion, because the partial pressure of oxygen would affect the minerals crystallizing in the crucible. Around the same time, that was 1955, around the same time, in the 50s and 60s, another very important variable that we've already mentioned today, water, was coming to the forefront in understanding the generation of continents. This is Yoder's lecture from the 1968 Andesite conference, and he was investigating the albite-anorthite binary. And here in yellow is his curve where he's showing temperature and composition here, albite to anorthite. And here's the 1 bar, atmospheric pressure liquidus of albite-anorthite. And we knew that if you increased the pressure to 10,000 bars, that the liquidus moved up. You needed higher temperatures to melt the rock. And what he was talking about in this lecture is he was noticing that you could move pressure up, but if pressure moved up from 1 bar to 150 bars, right, 2 orders of magnitude, but the pressure raise was in the form of water pressure, that the liquidus fell. So it's easier to melt rocks in the presence of water. And I think we all have some knowledge that this is true. We add an impurity. Right now, here we are in Vermont. What do? You salt your driveway. You add salt to your icy driveway. It lowers the freezing point, and your icy driveway melts at a lower temperature. So water is to rock as salt is to your icy driveway. Water causes the melting point of rock to lower, and that's what we're seeing here. Okay, so the conclusion in this lecture was the elevated water pressure effective at the beginning of crystallization of the rock may have delayed the appearance of plagioclase. Plagioclase crystallizes later in the presence of water. And he says calc-alkaline andesites are believed to be the partial melting product of the parental material under hydrous conditions. So in contrast to Kennedy, Yoder is now saying, let's not worry about oxygen partial pressure. Let's look at water. And if we suppress plagioclase crystallization, and water does nothing to when spinel enters the liquidus, we put spinel on the liquidus and we cause this trend of iron depletion in the presence of water. And Yoder made many plots of this type, and the reason I always choose this one is that he presented this at the Andesite conference. I don't know if you guys can see this, under the sponsorship of the Upper Mantle Committee. And I just want to know if, we could reconstitute the Upper Mantle Committee to fund my own research. That would be awesome. So let's look at oxygen fugacity now. It's a perennial topic of petrologists. We're always coming up with ways, if you want a job in petrology, you come up with a proxy for oxygen fugacity in rocks. Okay, and there's a million of them. There's the most straightforward, which is the ratio of 3+ iron to total iron. The more oxidizing, the more ferric iron you have. Okay, and this is not actually quite true in rocks because of crystal chemical controls, and we'll get to that a little bit potentially. But there are lots of proxies for oxygen fugacity. People might be familiar with magnetite-ilmenite pairs in volcanic rocks as a way to set the oxygen fugacity. I'm getting some nods. There are isotopic proxies. There are trace element proxies. Trace element, trace element, trace element, isotopic. Another speciation proxy, okay? Partition coefficient of vanadium, lots of them. Okay, so not all proxies work on all samples. You can only use the magnetite-ilmenite proxy if you have the minerals magnetite and ilmenite, right? And same with when we opened the talk with the spinel olivine OPX oxygen barometer. That works for mantle rocks, but it's not going to work in volcanic rocks necessarily. And when you compare some proxies head-to-head, they don't agree. And this is one of the things that is occupying some of my time right now. So in silicate melts, the 3+ to total ratio varies as a function of oxygen fugacity, temperature, and composition. And Ian Carmichael at Berkeley set this out beautifully. Much of his life's work was basically calibrating the relationship between 3+ to total ratio and composition and temperature. Thousands of experiments went into this calibration, and so we have a link for silicate melts, which we analyze as glasses. And this is a classic Carmichael study from 1991, where we have a lot of things represented here, but basically you have in white, let's just focus in white at ridges, and everything else, you know, here's a Kilauea, and then arcs, lavas of western Mexico, okay? Histogram, number of samples, and the delta NNO, this is like, you know, more oxidizing this way. Oh, I've got a little cheat sheet here, reduced this way. And you see that arcs, the lavas of western Mexico, are more oxidized than ridges. And so the big conclusion was arc rocks are more oxidized. Okay, and this is true. The lavas have higher amounts of ferric iron. And you can see this too when you look at magnetite-ilmenite pairs, okay, that this isn't just about arc rocks versus ridges. When we look at magnetite-ilmenite pairs in this classic compilation of Frost and Lindsay from 1992, it divides basically between calc-alkaline rocks, calc-alkaline systems, and tholeiitic systems. The oxygen fugacity recorded by tholeiitic systems is more reducing than the oxygen fugacity recorded by calc-alkaline systems across continents here. So volcanic rocks from convergent margins, calc-alkaline rocks, are more oxidized than those from spreading centers, tholeiitic. Okay, and we know this. So the question then, as I alluded to before, is the source of this dichotomy because the mantle is more oxidized beneath arc volcanoes? Or is this a process in the crust? Because at arcs, right, we're often erupting through thick crust. Is there a process of crystal fractionation, degassing, assimilation, that causes us to have this dichotomy that does not relate to the mantle beneath? So very clever work by Dante Canile in the late 90s, and this work was really influential for me. I was just starting graduate school in 1998, I guess, or 1999, and this paper had just come out. Dante Canile looked, and I know we have like, right, there's a vanadium department here, vanadium minerals, where it's at. Vanadium, such a special element for forming minerals because vanadium occurs in multiple oxidation states in the Earth, 2+, 3+, 4+, 5+, okay? So all these different oxidation states of vanadium possible in the oxygen fugacity range of igneous processes, okay? And so he did experiments where he looked at the partition coefficient of vanadium between olivine and liquid. Have an olivine in equilibrium with a melt, and you look at how much vanadium's in the mineral versus the melt. And under reducing conditions, the vanadium is all 3+. All right? And under oxidizing conditions, the vanadium's 5+. And the 5+ vanadium is like, get me out of here. I want nothing to do with this crystal. It's super highly incompatible in the olivine. So all the vanadium goes into the melt. Under reduced conditions, the vanadium is 3+. And it says, I still don't like the crystal very much, but I like it better than when I was 5+, so it's less highly incompatible. So the partition coefficient of vanadium scales beautifully with oxygen fugacity. Dante used this to his advantage and said, we'll scale this to an element, scandium, that is 3+ all the time to record oxygen fugacity, now using a ratio of trace element concentrations and chemically measuring speciation, how much sulfur is 6+ versus 2-, how much iron is 3+ versus 2+. That's hard geochemically. Measuring concentrations is easy. So he developed a trace element proxy for oxygen fugacity. This was applied in 2005 by Cindy Lee to arcs and mid-ocean ridge basalt. So you have two histograms here, arcs and mid-ocean ridge basalts. And Cindy Lee is relating the vanadium scandium concentration to oxygen fugacity using the experiments of Dante Canile. And what he found was really surprising and shocking for people. He found that these histograms overlap perfectly. And the conclusion of this study was that arcs and mid-ocean ridge basalts, while the lavas may have different 3+ to total iron ratios, and the lavas might be more oxidized in the case of arcs, the true mantle source during melting, set by the vanadium-scandium ratio, which is then, in theory, immutable to the time you analyze it, is showing us that the mantle source of MORB and arcs is the same oxygen fugacity. And this has huge implications for oxygen, the oxygen cycle on Earth. It says that the mantle wedge, the influence of subduction, the idea that you're subducting oxidized minerals or oxidized seawater, serpentinized altered oceanic crust, does not have any bearing on the oxygen fugacity of the mantle wedge that melts to make arc volcanoes, and that this work, the implication of this work and why this was such a big deal, is that arc lavas are more oxidized because of some crustal process that doesn't have to do with the origin of continents, for example, okay? And this, like I said, was not a one-hit wonder. And people were skeptical of this when it came out, but then there were a lot of other papers, and there were a lot of other trace element proxies, zinc iron, copper concentration, that seemed to support iron isotopes, the same conclusion that arcs and MORBs at the point of melting have the same oxygen fugacity. Mantle wedge, MORB source, same FO2. Okay, so, but we had all these other proxies, right, that seemed to say something else. So Osborne in 1959, during this whole Bowen-Fenner, how do we make calc-alkaline rocks, he said, you know, we've only reached a healthy and encouraging state of confusion. And he was writing about how do you make calc-alkaline rocks. Is it high water pressure or is it high oxygen fugacity? So this was the state in 1959, and we are still there. So what's the approach of this study? If it's all crustal processes, my collaborator Katie Kelly and I said, if it's all crustal processes, is there a sample from arcs that we can look at that would avoid the pitfalls, okay, of bulk sample 3+ to total analysis, okay? Can we look at mafic and minimally degassed melts? And one answer for that is olivine-hosted melt inclusions, okay? So here's an olivine crystal, a little bit of external glass clinging to it, and here is a melt inclusion. These are little aliquots of melt. As the olivine is growing in the magma chamber, the olivine seals up that melt and keeps it safe and sound. The volcano erupts, goes kaboom, degas, lose all your volatiles, massive degassing, massive, you know, you differentiate, other stuff's going on outside this olivine, plagioclase is crystallizing, other minerals are crystallizing, but this is sealed away at some more primitive state than the whole rock that you're analyzing at the surface. So melt inclusions are like little windows, little pictures that you're taking of the magma in the past, okay? And the other thing we did was we said we're going to go to the Marianas, not just because it was a margins-focused site, but because in the Marianas you had a ocean-ocean convergence. So you don't have pre-existing continental crust because we didn't want to worry about assimilation of continental crust, because if you have oxidized continental crust, you assimilate it into your magma, you're going to oxidize the magma. So we said avoid continental crust, avoid degassing, avoid crystallization, and our whole hypothesis was that if we could measure the 3+ to total ratio of these samples, that the two proxies would converge, that vanadium and scandium and iron 3+ to total, you would be able to resolve the Carmichael study and the Lee study by looking at these samples. And with laser ablation, ICP-MS, laser ablation trace element work, you can get the vanadium-scandium ratio of this melt inclusion. And the innovation that Katie and I had was to greatly improve and develop a way to get the 3+ to total ratio of this melt. Previously done by wet chemistry, bulk samples, hundreds of grams. Now there's a way to do it on experiments and on natural samples with a microbeam. So this is iron 3+ to total by Zanes, X-ray absorption near edge structure spectroscopy, if you're taking notes. Zanes, and this is a DOE facility. This is the National Synchrotron Light Source, where we've done work for the last decade. That facility is now permanently closed forever, and we're now working at the Advanced Photon Source in Chicago. Basically, this excites, you have an acceleration of electrons to relativistic speeds, and then they emit energy in the form of brilliant X-rays, very high flux, brilliant X-rays, which can be focused and you can have a specific wavelength selected for analysis. So we're moving through energy space of these X-rays, and we're looking at intensity. So this is absorption spectroscopy. I have my X-ray beam. I have my volcanic glass. I know the light going in. I analyze the light coming out. The light that is absorbed must be absorbed by the iron in my sample because I'm looking at the iron absorption edge. Very simple. It's just like taking an X-ray of your bones. This little feature here is called the pre-edge, pre-absorption edge, and I've expanded it here. And what you're looking at are a series of basalts that are equilibrated over many orders of magnitude in oxygen fugacity. This one has a lot of 3+ iron. This one has a lot of 2+ iron. So the spectra shifts with the 3+ to total ratio of these basalts, which were equilibrated in a furnace in my lab, so I know the FO2 they were equilibrated under. And I know the 3+ to total ratio because each glass has Mssbauer spectroscopy performed on it. Mssbauer spectroscopy is like wet chemistry. It's a gold standard for measuring this ratio on the bulk samples. And they also have wet chemistry too. They have everything. And so now with the microZanes beam, we can take a non-destructive microanalysis and get this ratio in a place that Carmichael couldn't, okay, on micro samples. And I'm just showing you here the real innovation of our work was not to develop Zanes. That was done by glass chemists and physicists beautifully, but was really to improve the resolution of the technique. We improved the resolution by an order of magnitude because we weren't interested in, does this glass have 30% ferric iron or 20% ferric iron? We wanted to know, does this glass have 21% ferric iron or 20% ferric iron? We wanted resolution on the same scale as Mssbauer and wet chemistry in the bulk. So this is an example of those same pre-edge peaks from the last slide, the background subtracted now, okay? So here's our 2+ and 3+ peaks. And I'm showing you here in black is a glass equilibrated at the quartz phaolite magnetite buffer. Here is a glass equilibrated at the quartz phaolite magnetite buffer minus half a log unit. And here is the spectra of a mid-ocean ridge basalt. Okay, so from here to here, we have only a half log unit. So you see, we really extremely excellent precision in our technique. And the calibration is as good to 0.005 in terms of 3+ to total values. So again, we went to the Marianas for this very specific reason of having an ocean-ocean convergence. This is from the this is actually not submitted. This is now published. The Journal of Petrology paper came out in 2014 in December. Mary Jo Brown's our graduate student, and she looked at all these volcanoes, Agrigan, Pagan, Alamagan, Guguan, Sarigan. These are all melt inclusions, olivine-hosted melt inclusions. We had previously looked at the back arc spreading center beneath the northern and southern Mariana Trough glasses. So now these are submarine basalts, just mid-ocean ridge basalts, except in the back arc. So some subduction influence, but not as much as the active arc, for example, when we look at trace elements. And this is a major figure, I guess, from her thesis. And there's a lot of information on here, and I just want you to get a few things out of this slide. The axes here are the 3+ to total ratio. More oxidizing things up here, more reduced things down here. These are error bars on the measurements. This is the MgO content. This is a proxy for how evolved an igneous rock is. Question? No. How evolved the igneous rock is. So basalts with a lot of MgO haven't had a lot of olivine taken out, so they have high MgO. As we fractionate, remove olivine, MgO falls. So these are all the mid-ocean ridge basalts in this field, gray field down here. These black triangles are the back arc basin Mariana Trough glasses, and you can see that most of them fall in the Morb field. But at a given extent of crystal fractionation, say 7 weight % MgO, some of them lie above the Morb field. They're more oxidized. All the points in color here are olivine-hosted melt inclusions. Okay? And the important takeaway point of this slide is that for a given, the same extent of differentiation, when you compare an ocean, a mid-ocean ridge submarine basalt with the same amount of MgO, to one of these arc melt inclusions, so they have the same amount of crystal fractionation, the arc melt inclusions are more oxidized. So we cannot call upon crystal fractionation, okay, to make them more oxidized, because at the same amount of crystal fractionation, they are already more oxidized. And nothing drives this point home more than looking at a blow up of this Morb field. This is all our data, published and unpublished. This is mid-ocean ridge basalts, all from mid-ocean ridges. What I want to show you is that generally there's a slight negative correlation. This was something that couldn't be seen in the wet chemistry studies because the precision wasn't there. But if we look at a single spreading ridge, like the Kane fracture zone in orange, where we have a wide range of MgO, you do become more oxidized, more 3+ iron as you subtract olivine, because 3+ iron won't go into the olivine. So as you subtract olivine, the 3+ iron builds up in the melt and gets higher. But this amount is just like 2% ferric iron across many units of MgO decreasing. And this slope of these orange points or the yellow points or the entire thing overall is very well modeled by olivine-only fractionation. And so we know that slope. And so when we look at this, we know this olivine fractionation slope, and we know that you can't get, say, from a primitive basalt, mantle basalt out here, and differentiate up to here along this slope, right? So these are inherently more oxidized. The primary magmas must be more oxidized. The other really interesting thing to come out of this study, which is also in this Journal of Petrology paper, oh yeah, here the reference is right, 2014, is that some proxies, okay, now we're converting those 3+ to total values into oxygen fugacity on this axis, and we're plotting them against trace element proxies like the thorium-lanthanum ratio, which it doesn't matter what it is. I don't want this to be like a geochemistry junk show. The idea is that thorium-lanthanum is a tracer for sediments, and there's no correlation. Barium-lanthanum is a tracer for fluids. Barium is fluid mobile, dissolves in water. Lanthanum doesn't. The higher the barium-lanthanum ratio, the more aqueous fluid influence the magmas. And you can see there is a correlation. The more slab fluids that are in these arc basalts, these rocks, the more oxidized they are. And we conclude that it is the aqueous fluids themselves that are doing the oxidation, that are the cause of arc rocks being more oxidized. And so this is an opposite conclusion, okay, to the vanadium scandium study. We're saying with this data would seem to suggest that the process of subduction itself, the delivery of oxidized, hydrated, altered oceanic basalt, dewatering and influencing the mantle wedge, is the fundamental reason that arc rocks are more oxidized, and that you don't need to call upon assimilation, degassing, fractional crystallization, some shallow crustal process to do this. That this is about the global plate tectonic cycle and the global oxygen cycle, not a local process. That's conclusion 1 of this talk. Done. Primitive basalts erupted at arcs are more oxidized than ridges. Okay, we knew that. Carmichael, we knew this. But what we're adding here is that crystal fractionation and degassing can't really account for this. Okay, so we get the same histograms that Carmichael got in 1991 using a different technique on different samples in a different part of the world. Okay, so wait, but what about this proxy, vanadium scandium? So I, as a scientist, am still really interested, you know. It makes so much sense. You know, I love Dante Keneal's work. I love the idea of vanadium scandium as a proxy for FO2. It's elegant, beautiful, the experiments, you know, why, so if our data, you know, the outcome of our study was not what we predicted. We thought that our data were going to converge with vanadium scandium, and we were going to be like, look, it's all one big happy answer, but it didn't. So what's going on with vanadium scandium? So I'm going to show you quickly now some experiments have run recently in my lab. And the piston cylinder device, which is a device capable of going to 4 gigapascals, so at 5 orders of magnitude higher pressure than we're under now. We're now looking at those pressures where the mantle is melting to generate basalt. So don't worry about any of these details unless you're the kind of person who worries about those kind of details. The bottom line is that these experiments are on arc-like compositions with arc-like amounts of water and carbon dioxide, and the minerals, olivine, clinopyroxene, orthopyroxene, spinel, plus or minus plage, the minerals that would be present in the mantle that's going to melt to generate arc rocks, okay? And in these experiments, we tried to control the oxygen fugacity. Turns out oxygen fugacity, I just believe, cannot be controlled. It's like a free spirit parameter, okay? It's not like temperature. It doesn't play by the rules. But using Zanes, we can now measure the 3+ to total ratio of glass in our experiments. It's just like revolutionizing. You no longer have to say, oh, I think the oxygen fugacity of my experiments was about this. You can say, no, I know what it was because I can measure this. And the Kress and Carmichael calibration is valid in this experimental context. So we're going to look at vanadium-scandium partitioning. Here's a charge. This is an olivine capsule. You can see this is 5 millimeters. Sense of 5 millimeters there. This is a noble metal capsule with an olivine capsule inside, kind of like, I'm kind of into this, like, it's like Russian doll, something inside something, okay? The basalt is inside the olivine capsule, and down here, we have our friends nickel and nickel oxide. So we're trying to set the oxygen fugacity, okay, in the charge to control the oxygen fugacity here in the melt. Now, if I do a thin section, essentially, make a wafer of this experiment, here's the olivine capsule in white, all washed out. Here's my beautiful window of glass, nice brown glass, some big fat orthopyroxene crystals, and then this mat of clinopyroxene crystals and spinels. So I have my assemblage, I have my glass, I can run my X-ray beam, zing, right through there, get my 3+ to total ratio, know my oxygen fugacity. When we do have olivine OPX and spinel in equilibrium, we find that those two barometers, the Zanes proxy and that mineral proxy, basically agree. But because we don't always have all those phases, for the rest of the talk, I'll just be presenting FO2 in terms of the Zanes result. We only had 4 experiments that we were able to look at both proxies. Ignore most of this. I want to just focus in on this plot. You can, if you're quick with geochemistry, you can look at all the plots, but let's just look at this one. What I'm plotting here is that same thing Dante Keneal plotted, the partition coefficient of vanadium between a mineral and its melt. Here's orthopyroxene. So vanadium, okay, becoming more, as you become more oxidized, becoming more incompatible. These circles are the vanadium partition coefficient between orthopyroxene and melt. And you can see vanadium becoming more incompatible as the 3+ to total ratio of the melt. As the melt becomes more oxidized, the vanadium is becoming more incompatible. The diamonds are scandium. Scandium does nothing, and it should do nothing because it's always 3+. It can't be another oxidation state. So our experiments are behaving just the way we would expect them to and want them to from all of Dante Keneal's work. And we see the same thing in CPX. Big movement on the vanadium partition coefficient, no movement on the scandium partition coefficient. So now we can ratio these things. Here's Dante Keneal's work. This is the work that I showed you before. It looks a lot more scattered here next to Hugh O'Neill, Guillaume Malman and Hugh O'Neill's work. You know, they do these 1 atmosphere experiments, beautifully controlled, very clever. I want you to notice that the oxygen fugacity range, the reason they have beautiful control here is like the whole Earth happens like right here, okay? But they can fit this beautiful functional form, a very elegant study by doing experiments way out in like planetary la-la land. Keneal's experiments on there for scale. Maybe there's a compositional effect, okay, because these are simple system, these are natural system. Oh my goodness, but here's our data, okay? Higher pressure, water, it's offset, okay? It's offset to the side big time. And this is just the partition coefficient of vanadium. It's a little hard to think about. Here's scandium. Scandium, of course, just a line. I could have shown the points, but just makes for a messy slide. Scandium at 1 atmosphere. Scandium in the experiments run in my lab, and you can see that it shifts as well. So both these trace elements are shifting. What really matters to how this proxy works is how their ratio shifts. So in this next slide, I just wanted to show you the raw data. Now I'm taking a ratio of those two partition coefficients. I'm looking at the ratio of the vanadium one to the scandium one. And these data are still offset to higher, more oxidizing oxygen fugacity. And if we zoom in, it might not look like much, but if we zoom in right here, okay, we can see that for a given ratio of the vanadium-scandium partition coefficient, you would get a different by an order of magnitude oxygen fugacity using the calibration from my lab versus this 1 atmosphere dry simple system calibration. An order of magnitude difference in oxygen fugacity, which by the way is like the difference we're talking about here, okay? So this is based on modeling done by Cinti Lee. And this is to put it into like real terms for like the field geologist. You pick up a rock, you measure a vanadium-scandium ratio of 6, okay? And you look at a vanadium ratio of scandium of 6. It doesn't matter what the melt fraction is. I can melt 1%. I can melt 20% of that rock. Vanadium-scandium ratio of 6 corresponds to QFM minus 1, okay? That's based on the 1 atmosphere dry melting relations I just showed you. But using our calibration at high pressure with water, everything shifts. And now that same rock with the vanadium-scandium ratio of 6 that you measured, you now interpret as having an oxygen fugacity an order of magnitude higher, 0. Okay? So the implications here are that if one calibration is appropriate for ridges and the other calibration is appropriate for arcs, you could come up with, for the vanadium-scandium ratio, this order of magnitude offset just through trying to apply the same calibration to 2 different systems when it doesn't apply. And this also has implications for the Archean, because Dante's whole thing was applying this whole vanadium-scandium calibration to Archean rocks, okay? And I don't want to speculate on what, he did his experiments on komatiites. That's a great idea when you're looking at komatiites, right? So the 2 major conclusions here are we think that this is a source signature, okay? And we think that the vanadium-scandium ratio is promising, it's elegant, it's beautiful, but it probably needs more calibration work to tune it enough to get really meaningful data for the scale of FO2 differences that we're interested in as earth science, as terrestrial petrologists. And now in my last 5 minutes here. Is that all right if a 45-minute talk, okay? Okay, good. My computer tells me I've been speaking for 40 minutes. So in the last 5 minutes, I'm going to tell you about upcoming work and where we're taking this next. And I'm here as the GeoPRISMS lecturer, and I'm going to tell you about my up-and-coming GeoPRISMS study that relates to what we've been talking about the whole time here. Another beautiful study, Mindy Zimmer, 2010. This is Terry Plank's graduate student at Vermont. And what they did in this study was they defined something called the tholeiitic index, okay? They wanted to come up with a number to quantify, am I doing this or am I doing this? And so what they did was they looked at 2 classic volcanoes in Alaska, Augustine and Shishaldin. And the data for Shishaldin and Augustine at 7 weight percent MgO, relatively primitive for an arc rock, overlap in FeO content. They have similar iron contents at 7% MgO. Then Shishaldin proceeds to go like this before going like that. And Augustine just plummets straight down, trend of pure iron depletion, such as by the time you get to 4 weight percent MgO, the Shishaldin rocks have a ton of iron, and the Augustine rocks have very little. And so they came up with this ratio, or index, the tholeiitic index, and they said it's going to be the ratio, okay, of the amount of iron at 7% MgO, or a ratio of the amount of iron at 4% MgO to the ratio of the amount of iron, concentration of iron at 7 weight percent MgO, such that a high value means you're really tholeiitic, your trend of iron enrichment, and a really low value means you had a trend of iron depletion. You're really calc-alkaline, and they call this a tholeiitic index. And the brilliance in this study was that they looked globally at rocks from all over, mid-ocean ridge basalts here in black, and arc rocks, and ocean island basalts, and they found this beautiful hyperbolic relationship with water. Here's Augustine out here, really wet, really calc-alkaline. Back here we have the East Pacific Rise, really dry, really tholeiitic. So this goes back to Yoder, right? The more water you have, you suppress plagioclase crystallization, okay? And you allow spinel to come on the liquidus, or you don't, in this case, you don't have any water, you're dry. Plagioclase crystallizes like gangbusters, and you have this trend of iron enrichment. Out here at Augustine, you suppress plagioclase crystallization, spinel crystallizes, and you have a trend of iron depletion with water, Yoder-esque. What we see in our data for these same places, okay, a lot of the same places, we're now looking at the ratio of 3+ to total iron corrected to 6 weight % MgO, because remember I showed you that 3+ to total varies as a function of MgO content in a very predictable way. And we're plotting that against the tholeiitic index. And what do we find? A beautiful correlation. We find a beautiful correlation between the most oxidizing volcanoes, all right, are the most calc-alkaline, and mid-ocean ridges are reduced and tholeiitic. Back arcs are a little bit in between, the Marianas are somewhere in between, and form trends form some kind of array. We can look globally at this. So this is a nice correlation too. Now, so that'd be great. You'd say like, okay, we know water is important, but maybe oxygen fugacity is an underappreciated variable when we're talking about the tendency of a rock to crystallize along a calc-alkaline trend. The big problem we have in this data set is that water and the 3+ to total ratio are correlated. And I think that some of you were asked to read a paper of ours before my coming. I was like, incredibly nice, so that everyone was prepared to take receipt of the FO2 message, I guess. And this is updated data from that 2009 science paper where we showed this relationship between water and oxidation state. And it's really, really important if you have one take-home message from that paper. It's not that water is an oxidizing agent. Water is not an oxidizing agent. It's oxygen fugacity neutral. The idea is that water might be carrying oxidizing agents, dissolved O2, sulfur, whatever. There's many, many. We don't know what it is, okay? But these are beautifully correlated, these two variables. So how can we tease apart? How can we disentangle who the primary driver is? Oxygen fugacity or water? And why would we care? Okay, that's always always ask yourself, why does anybody care? The reason it matters who the lead actress is that if high oxygen fugacity is the main driver of generating continental crust, then in an Earth history or planetary sense, we need to think about how we can deliver oxidized materials into subduction zones in order to get continents. Okay? If water is the driving agent, then all we need to do is find a way to introduce water, okay, and we think that there was a time with like anoxic oceans, for example, right? So these two things in Earth history or on planets generally are not necessarily correlated. And so we're trying to understand, you know, if the tholeiitic index, if we have mid-ocean ridge basalts, back arc basins, ocean island basalts, and arcs, and this relates to water or this relates to oxygen fugacity is really important from a process sense and a planetary evolution sense. And so that's what we're really trying to do with our GeoPRISMS study, is tease apart these two highly correlated variables in modern volcanic systems. So where we're going to go is the western Aleutians. The Aleutians, very, very big, very, very big. So like New York to California, big. This little box here around these islands that I'm going to, this coming September, this is 650 kilometers. So the Aleutians are at a very, very large scale. And the reason to go to the western Aleutians, to this last volcano out here, Bull Deer, it's my target. Geologists, we haven't been there in a long time. There's a kind of bird that only lives on that island. And so, you know, landing the helicopter there is not straightforward with fish and wildlife, for example. We're trying to work with conservation to make sure that we don't disrupt nesting while we're sampling. But we really want rocks. We really want volcanic tephra from Boulder, which is super calc-alkaline. And why is that so interesting? Here you are, just like the Marianas. You're on an ocean-ocean convergent margin. There's no continental crust being assimilated into these volcanics. And yet, they are some of the most calc-alkaline volcanoes on the planet. Okay? When we plot them up in terms of this tholeiitic index, of which you're now familiar, against longitude, we start here in continental Alaska. Calc-alkaline volcanoes, you betcha, we're on the continent. We expect to find calc-alkaline rocks erupting through continental crust, okay? You move off the continent into the eastern Aleutians, and you get tholeiitic, you know, as tholeiitic as mid-ocean ridge basalt, you get tholeiitic volcanoes, okay? We expect that, ocean-ocean convergence. We get more tholeiitic volcanics. But then you go further west, and suddenly, who are these guys? What is happening out here? How are we getting such continent-like rocks way out at an ocean-ocean convergent margin? And this is like, you know, it's been called by Peter Kellerman like the nursery of continental crust. If we could understand the formation of these rocks, we might unlock the secret to how continents are generated. And so we're going to go out, but there are no appropriate tephra samples. Volcanic tephra, what we want are melt inclusions, rapidly quenched, naturally glassy melt inclusions. So we're going to travel out to these islands in the far western Aleutians to collect tephra to look at the water contents of those melt inclusions and look at the oxidation state of these melt inclusions, because there are some out here where, based on the preliminary data we have, the water and the oxygen fugacity are not necessarily correlated, or the water, rather, and the tholeiitic index are not necessarily correlated. And you can see there's some big changes along the Aleutians in terms of the convergence rate, here in green, the sediment flux, okay, plummeting out there. So we also want to use isotopes and other kinds of geochemistry to not just get at who's in charge, but what is the process? What is being subducted there, or what is melting there? What is the process by which these calc-alkaline magmas are being generated out in the western Aleutians? And so that's my upcoming work in Alaska this summer. And I would be remiss without thanking, of course, GeoPRISMS. I'm sorry, I have margins on here. GeoPRISMS is the successor to margins. I should have changed the slide. And thank Katie Kelly, my collaborator, in all of the work I've presented at the University of Rhode Island, and all the collaborators at other universities, postdocs and graduate students, and everyone who has sent me samples so generously. So thank you very much for listening, and I'll take questions. Can't tell if no one interrupted me with questions. I always think that's a bad sign. So I'm going to complete glazed sign. Yeah.
I think, if I remember from Roger Burns' work, Roger Burns here, vanadium 3+ has a very strong crystal field stabilization energy in magnetite or spinels. Would that affect the vanadium 3+ in the magma if there's co-crystallization?
Yeah.
But I think, somebody at Thing Molly showed that. Would that affect the vanadium scanning?
Yeah, so right, vanadium is really compatible in magnetite, in spinels, magmatic spinels. And you can see that in vanadium data. You start to crystallize and you see that drop in vanadium. So it's interesting you say that. Cinti Lee would say that the vanadium scandium proxy should not be applied to magmas with less than 8 weight% MgO. That makes it really difficult to apply that proxy to arcs, because there aren't that many arcs that erupt magmas with more than 8 weight% MgO. The idea is that vanadium scandium, however, is not sensitive to crystal fractionation. And this has been shown not to be the case since. I mean, there was a study by Muriel Lobier just a couple of years ago with Tim Grove and Charlie Langmuir showing that it changes, and that maybe vanadium, I think ytterbium would be more stable with crystal fractionation in ocean, in Moore. So if you have, that's exactly right for vanadium scandium, if you have a lot of magnetite crystallizing out maybe on the liquidus first, and maybe it's not even, in the hand sample that you analyze, but could have affected the vanadium scanning ratio. This is something we'll be looking at, for example, at Augustine.
So
It's a great.
how do we get under
Oh yeah, you can be on my list, sure. You can practically be on the ship. We're going on a small, very small boat to the Western Aleutians that has a helicopter, so it's going to be helicopter assisted. But the helicopter pad is like smaller than my desk at work, so I'm kind of nervous about the whole thing at this point. But trust NSF and their contractors.
Question about your oxygen fugacity experiments. How long do they take? I mean, is it
Several days.
Several days?
So they go in. You sinter them for a little while at low temperature to close the pore space so that when you melt, it doesn't just is the technical term. And then we put the temperature up above the liquidus, or we want to destroy a bunch of the nucleation sites, because one of the big goals, that's a hard goal to achieve, is achieving crystals that are big enough to laser. So we need crystals that are at least 30 microns across, and this is not trivial for many phases. And so we ramp the temperature down over 5 or 7 hours, and then they sit for somewhere around 18 hours at those high temperatures. And so almost no experiment in the world is at equilibrium. I think any experimental petrologist to claim otherwise is probably right. There's no such thing as equilibrium. We like to think we're approaching equilibrium, and we can do tests for the approach to equilibrium. How systematic the data are is one thing that makes us feel good about in this much more difficult setting of high pressure hydrous versus the 1 atmosphere, and that the systematics and the fact that you need to look at mass balance. You can look at a lot of different things, zoning, to hope that you're approaching equilibrium. They run for several days, though.
And they all have water.
All high pressure experiments have water, even the ones that are anhydrous. The question is how much water. So nominally dry experiments still have water, but these go up to 5 to 8% water in the glass, so they get pretty juicy in there.
You say that rock has the capacity to withdraw oxygen from H2O. If so, what would be the primary driver? Exothermic or endothermic?
Yep, so it's missing the eraser, but that's okay. So we can think of H2 plus 1/2 O2 goes to H2O, okay? So hydrogen and oxygen on one side, molecular water on the other side. So you can imagine, and for example, in the early Earth, if you dissociated water and lost the hydrogen diffused away independent of the oxygen because it diffuses quickly or something, and you lost the hydrogen as hydrogen gas. This is similar to during the process of serpentinization of rock. The hydrogen is lost as gas to the ocean, leaving behind a rock that is more oxidized. In the early Earth from a magma ocean, you could dissociate the water, lose the hydrogen as hydrogen gas to space, and leave the planet, say, more oxidized. So degassing water, H2O, doesn't do anything to change the oxidation state of a magma, because H2O is FO2 neutral. It carries no charge. And this has been shown beautifully by Becky Lang in the University of Michigan, some recent studies of andesites, just gorgeous work, kind of empirically showing this. But theoretically, we can also know that it's true. What is interesting is that if you dissociate water under really reducing conditions, you do make that hydrogen gas that if it were to escape, might oxidize the rock. However, as that hydrogen gas escapes and things get more oxidized, you don't dissociate as much water to hydrogen because the higher oxygen fugacity pushes the equilibrium back to water. So it's a self-limiting process. So beyond around QFM0, the process stops being efficient as an oxidizing mechanism. So I think that water can and does, by some equilibrium constant, is always dissociated in melts, right? It's some combination by the equilibrium constant of H2, O2, and H2O, or OH, okay, species. But the balance, equilibrium balance is determined by the KEQ, and I do not think it's an effective means. If you just add water to a rock, right, at a given FO2, it does not make a more oxidant. It doesn't raise the amount of 3+ iron, for example. Am I getting at what you're getting at?
The driver. Is it entropy? Is it
The driver of
the reaction, the release of the oxygen from the water? The primary driver, as you say. You use that phrase, primary driver. That's what I'm looking for. That would disassociate that oxygen.
Well, so there's always an equilibrium between those, just like in any chemical reaction, there's some equilibrium constant. The equilibrium constant, is affected by the composition, the temperature, right? So the high, so for example, there's a pressure would drive the reaction one way, temperature might drive the reaction another way, but the primary driver is the oxygen, the partial pressure of oxygen itself. When you add more oxygen, you're going to drive it towards the molecular water side. Is that
Need is the primary.
need?
Requirement. An absence of something.
In all chemistry, like it's a chemical potential.
Well, one quick question. The sort of the last graphs that you showed, the Foley index
yeah.
versus the different things. There was one outlier on those.
Yeah, pericatine.
Yeah, I was just curious about that. Is
Yeah,
it
so-
analytical or is there something interesting
what we
about
really
that?
want, we'd love to have. So these are individual melt inclusions and samples. So Morb is representing many samples here. Okay, we're showing a lot of samples here represented by Morb here. But this is one melt inclusion from pericatine. And so what you really want, if we go back, okay, what you really want to do is do something like this. Okay? So for example, if we look at aggregate here, these data in blue were published in a 2012 EPSL paper. And what we have in the aggregate data are many melt inclusions from a single eruption of this volcano, representing a single liquid line of descent from 5 weight % MgO to 3.5 weight % MgO. And we can say that during that liquid line of descent, the melt inclusions didn't get more oxidized, they actually became more reduced. And that paper is all about how sulfur degassing was the driving force in reducing those along that liquid line of descent. And here's Sarreguin, Pagan. What you really want is to look at 20 melt inclusions from pericatine, from a single eruption, and see so for example, if we go back to that now, okay, if we go back to looking at pericatine on any of these plots, we want to say, is there a liquid line of descent? Is it like this? Is it going, is there some kind of trend? We have no context for this one data point. So the power of this study, like anything, is it's a global compilation, but we don't read too much into any individual point, and we assume that, maybe this is an outlier from pericatine. We don't know. We would love to have more data, as all scientists would, from all the volcanoes.
Are the olivine melt inclusions pure glass, or is something starting to crystallize?
So the melt inclusion is glass trapped inside an olivine crystal.
But
They
not-
never have daughter crystals.
Okay.
We throw those out of hand. We never analyze. If we analyze them, it's by mistake, and we discover they have daughter crystals later. We want to look. We never re-homogenize. We never reheat. We try to look at ones that don't even have vapor bubbles. We try to look at naturally glassy, naturally quenched, rapidly quenched, daughter crystal free. Can't always get vapor bubble free, but we try to look at them in pure smooth conclusions.
Do you have time series data so that you know if as you're drilling into the crystal because of the laser,
We expose them fully, so we never laser the crystal, and the Zanes never goes to the crystal. We make double-side polished wafers, and the IR spectroscopy for the water and CO2, the Zanes, the laser, the microprobe is all directly through the glass. So we work very hard to make sure we don't have crystal interference. It's a big, like, lab procedural thing that we do. Because that would really screw you up, because the olivine is all 2+ iron, and devoid of all the trace element goodies, it would be bad. So we'd work hard to not have olivine interference.
That's painstaking.
My guys, don't let this be the only lecture I've given in like 5 years where no student asks a question. Don't let UVM go down that way. Do something. Somebody do something.
So the Zane stuff seems really cool and exciting that you've gotten it so that you can look at, iron oxidation states. Is there a thought of doing other metal oxidation states? Like,
Yeah,
could you
Zane's
look
is
at?
just boomtown right now.
Okay. Because could you look at vanadium oxidation states? Or
Yep.
is the concentration so low?
Yes. Vanadium is super interesting. People have looked at calibrating vanadium redox itself. And yeah, I get a lot of calls about vanadium because the problem is when you go to higher pressures, the peaks themselves just disappear and we don't know why. Or maybe someone knows why, like right now, but that hasn't made it, like either through the grapevine or through the literature to me yet. Chromium, europium. You'll be seeing papers, if you look, if you were to go back to Google Scholar right now or ISI, you'd see tons of paper on chromium oxidation state, europium oxidation state with discussions about the FO2 history of the planet, of the moon, of individual zircons from the Archean. It has just been boomtown the last 5 years in Zanes, I would say.
So you can, even though those, like, what type of concentrations do you need
With a
in order to
synchrotron, we're ppm, man.
Okay.
It's just beautiful. At the advanced photon source, the beam is so brilliant, the flux so high that you can run natural samples with natural concentrations. So you can see some of the scientists at GSE CARS, Sector 13 at APS, or even National Synchrotron Light Source, which has a bigger spot size and lower flux. I mean, doing beautiful maps of like plant seeds and mouse brains. I mean, anything you can. It's beautiful work. Oh, and Zane's, I think, goes way beyond the earth sciences. You saved it.
Any more questions for Liz? Please join me in thanking her so much again.
Thanks.